try to cover as much as we can in the time that we have. So we were discussing linear hydrodynamic stability, and I had said that if you have any dynamical system like this, where this f doesn't depend on time explicitly, okay, f is changing, the value of f is obviously changing in time, but it is through y. F is not explicitly changing in time, it is not an explicit function of time. So these are called autonomous systems, and if you have these kind of systems, then we made all our derivation and discussion that there is a stationary or base state f of y naught equals 0, and then we said that okay, if y is some y naught plus epsilon y prime, where this epsilon is much less than 1, and some norm of epsilon y prime over some norm of this guy is also much less than 1. So this is the condition for linearization. Okay, in some textbooks you will see it written like this. Okay, so in some books, or even if you look at some papers, you will not see an epsilon written. People will say, okay, there is a perturbation to your base state. There is a perturbation to your base state, and the perturbation is small. Okay, the perturbation is small. So this, both of these basically are same statements physically, that we are adding small perturbations. We are adding small perturbations to base state. Okay, we are adding small perturbations to base state y naught, and we are looking at the dynamics of those small perturbations only. Okay, we are looking at the dynamics of those small perturbations only. So in that case, you have, when you substitute this here, you say that this is dy prime by dt, and on the right hand side you had del f over del y evaluated at y naught times a y prime. Okay, we wrote this as a J matrix or the Jacobian matrix. We wrote this as the Jacobian matrix, and from here we said that you can diagonalize this Jacobian matrix. Okay, let us say this is diagonalizable. I am not going to go into details. If this J matrix is non diagonalizable, then what happens? So let us diagonalize this Jacobian matrix and see what we get. So we wrote this as V times lambda V inverse, where this lambda matrix was a matrix with diagonal entries as eigenvalues and rest all 0. So this was a diagonal matrix. Okay, and then we said that if you define an x which is V inverse of y, then you can write dx by dt y prime, sorry, is equal to lambda times x. Okay, so here what we had was, this was our decoupled linear system. So this is decoupled linear system, this is coupled. Okay, so as a result of this diagonalization procedure, I have decoupled my system of equations, and then I had said, okay, since these are decoupled, you can look at individual solutions. So xi in time will look like xi at time equal to 0 e to the power lambda I t. That is what the solution of this equation will be, since lambda is our diagonal matrix. So this is what you will get, not summed over I, no summation over I. Okay, there is no index notation here. So this is what your individual component of this x, how they will evolve in time. So if any, or we had written it like lambda sub superscript I to emphasize there is no summation. So if any lambda of I has real part which is greater than 0, then that particular xi will be growing exponentially in time. So in that case, what you say is that the norm of this x vector in time is growing e to the power lambda real of this, and you can take a max over I t, because there may be 5, let us say you have a system of 10 degrees of freedom, you have 5 eigenvalues which have real part positive, and so whichever one of them has the maximum real part, positive real part, that is what you will see, right? If I give you e to the power t, e to the power 2t, e to the power 10t, after later times e to the power 10t will dominate. Okay, so whichever one has the maximum of the real part, that you will see after some time. Okay, so this is called linear instability. This will be linear instability that you have looked at. Okay, this is called linear instability, and so we are going to look at this in PDEs. Now, when we look at this in PDEs, because for fluid mechanics the governing equations that we have are partial differential equations. So, for PDEs we have coupled system of PDEs basically. Okay, so let us say for fluids we have coupled system of PDEs. Okay, now once you have a coupled system of PDEs, then what do we do? How do we convert it into a system of ODEs? That is what you are going to see in a moment. Okay, we will perform similar linearization. We will do similar linearization. Okay, then we'll convert our linear PDEs. We'll convert our linear PDEs to ODEs. We'll convert our linear PDEs to ODEs using something called a normal mode assumption. Okay, using normal mode assumption. Now, what is this normal mode assumption? So, instead of talking about its theory, I will exemplify this with an example. Okay, so let us look at an example. Let us look at not the simplest example, I would say, but not the most complicated example also of hydrodynamic instability, and it is called Rayleigh-Plateau instability. Okay, so if you have seen very thin jet of water falling from a tap, you might have seen that after some downstream distance it starts to break down, and then it starts to break down into droplets. Okay, now why does this breakdown happen? This breakdown actually happens due to this instability, and as you will see that given some thickness of that jet and velocity of that jet, let us say, you will be able to calculate what will be the starting size of those ripples that form and which will be the approximate frequency at which your droplets fall down. So, you can calculate that frequency of the droplets falling down using this Rayleigh-Plateau instability. Okay, and the physical, very crude physical, let us say very crude physical explanation goes something like this. Okay, so let us say you have a water jet that is falling down. Okay, forget that it is falling down with gravity or accelerating or anything. Let us say it is just moving with a constant velocity downwards, that is u. So, you transfer yourself in a frame of reference that is moving with this u, and you see a stationary water column. Okay, you see a stationary water column. Now, this is a water column and it has surface tension. Okay, this is a water column and it has surface tension. Now, let us say I add some perturbations to this water column. Let us say I add these kind of perturbations to the water column. Let us say I pinch the water column a little bit. Okay, then what you can clearly see here is that due to this pinching, due to the shape that you have changed, you can imagine that the pressure here is larger. Okay, pressure here is larger than here. Okay, so if I let us say this is P1, P2 and P naught, you can say that okay, P1 is greater than P naught. And due to the shape, you can say P2 is less than P naught. Okay, due to the shape you say P2 is less than P naught. Similarly, here also you will have, let us say, P1 which will be greater than P naught. Okay. Now look at the pressure gradients that are forming. You have a high to low pressure, then a low to high pressure. Okay, you have a high to low pressure. Okay, what will be the direction of flow here? So if you are pinching it like this, there will be flow that is happening like this. Huh? So that means the moment you pinch, the fluid rushes out of that pinching zone, and after some time the fluid will keep rushing out of this pinching zone, and you will see this pinching grow in time, and eventually you will form a droplet. This is the crude physical explanation. We will see that how we will see that play itself here in a moment with all the mathematics. Okay. So what we are going to say is a water column, there is a water column. So given this is what's given, there is a water column or any fluid column to be general, okay, in air. So there has to be surface tension with surface tension coefficient sigma. Okay, let us say the column's radius is some a. Okay, water column has radius a. Okay, and we are required to get the stability of this water column. Okay, so we ignore any viscosity. Let us ignore any viscosity. So ignore viscous stresses. So let us look at purely inviscid flow. Now you may think, okay, so many things you have discussed about inner outer layer and inviscid viscous flows. You will be right in questioning all of that, and I am saying let us for a moment accept that there is no viscosity and move on with the analysis. It is a simpler analysis. Of course, in reality you will have to do this analysis with viscosity within some approximations, and notice that now you have another coefficient appearing. So it is not just the Reynolds number being large or small where your viscous stresses will be negligible. You could also have cases where your viscous stresses are not negligible compared to inertia, but they may be negligible compared to surface tension forces. Okay. And so then in that case you cannot say viscous stresses are negligible compared to inertia. Sorry, you cannot say inertia and viscous stresses are of the same order, because in that case you will see inertia and surface tension forces will be of the same order. So these kind of numbers are called Weber. This is a dimensionless number called a Weber number that you can make, and Weber number basically quantifies the ratio of, I think it's one of them, I don't remember which one. It is either, you can look it up in literature, either it's the ratio of surface tension forces to viscous forces or vice versa. But the idea here is that let us say we are in a regime where we can ignore viscous stresses. Okay. So in that case our governing equations are something like this. Of course, we are looking at incompressible flow. We are looking at incompressible flow. So del dot u equals 0. Okay. This is our governing equation, and we have del u over del t plus u dot grad u plus grad p by rho equals 0. This is all inside water column. Now we also have, as you can imagine, we have interface. This is the water column, this is a cylindrical water column, this has an interface, and we are considering surface tension. Okay. So we have dynamic interface conditions. So dynamic interface conditions are what? Dynamic interface conditions are what? So let us say we say that this is pressure P naught, and this is, so P1 P2 is just at some different points 1 and 2. Let us say the pressure inside is P that we have written. So what is P going to be? P is going to be what? Let us say P minus P naught, or we are going to actually denote this with P infinity, okay, because P naught, the subscript naught I am going to use for base state. So P minus P infinity is going to be what? Sigma times del dot n, okay, which was the curvature. What is the radius of curvature? What is the curvature for a cylindrical surface of radius a? This was mean curvature, remember. This is simply 1 by a, okay. This will be simply 1 by a. P minus P infinity is sigma by a here, okay. This is our dynamic interface condition, but it won't be. So, n hat, you can imagine n hat will not be simply your E hat r for a deformed state. In the perturbed state, you won't have E hat r. So, that is why this is, so 1 by a is true for the base state, and this is our general equation for any geometry. And of course, we have the kinematic interface condition, and the kinematic interface condition is that you have, let us say, the surface is given by, so this is radius, okay, this is r, and let us say this is z, okay. So, the surface is given by r equals some capital R as a function of z comma t, okay. So, the kinematic interface condition basically says that actually it will be a function of theta also, let us consider it a function of theta as well. So, kinematic interface condition says that d by dt of this r minus theta t equals 0, okay. So, this is an implicit equation of the surface, okay. So, r minus capital R equals constant is the implicit equation of the surface. So, since this is a constant, I am saying d by dt is 0, okay. So, this is our kinematic interface condition. Now, let us first solve for the base state, and this is a let us say I am also exemplifying you, in front of you how to attack any instability problem, any hydrodynamic instability problem. First, write down all the governing equations, okay. Write down all the interface and boundary conditions. Here there is no other boundary, okay. The fluid column is separated with air through this interface, so that interface condition is all we need. So, let us first write down all the governing equations and boundary conditions, then first identify and solve for the base state, then do linearization, okay. So, the steps should be in this logical order also. This will minimize the amount of mistakes that you may make, okay. So, let us solve for the base state. Remember, base state was stationary state, okay, and stationary state is very obvious here. The stationary state is very obvious, that is this r z comma theta comma t is simply equals to a, which is a constant, okay. As a result of that, our pressure inside the cylindrical column is simply P equal to P, or let us say R equals this. P is P infinity plus sigma over this capital R, which is or sigma over A simply, okay. Capital R is not going to be your radius of curvature, okay, that is just radius, that is radial distance of the interface, and u is 0. That is it. Your base state is as simple as that. You have constant pressure which is slightly higher than the atmospheric pressure inside the control inside the water column. You have R which is constant, the radius of the water column is constant, and you have 0 velocity. So, the base state is very straightforward. Then we proceed with adding perturbations. Now, add perturbations to it and linearize all equations. So, when I say all equations, it means the governing equations as well as the boundary condition equations. Here we do not have any boundary condition, we just have an interface condition, okay. So, let us do that. So, let us say our R is basically, which is this R of theta comma z comma t, is a plus some epsilon c, let us call it c prime theta comma z comma t. Okay. Let us add perturbation and linearize all equations. We are adding the perturbation to first the radius. As a result of this perturbation in the radius of this column, we are saying the velocity becomes some epsilon u prime and pressure becomes P infinity plus sigma by A plus some epsilon P prime. Okay. Now, this epsilon P prime is something that we can derive from the general relation of our interface condition, and that is that this P should be P infinity plus sigma del dot n, and it is this variation of n vector, the del dot of this n vector, that is causing your pressure to deviate from P infinity plus sigma by A. Okay. So, let us first compute this del dot n. So, n in our case, now that we are looking at it in radial coordinates, n will be given. So, n usually is simply given by this, right, where this f is the implicit equation for our surface. So, we have grad of r minus a minus epsilon c prime over mod of this. Okay, I am not writing it again. So, that is our n vector, this is gradient. Okay. So, writing the gradient, we have, let us say, so none of these are functions of r. So, we will have e hat r. So, maybe let me write it down clearly. So, you have e hat r del by del r plus 1 by r e hat theta del by del theta plus e hat z del by del z. Okay. That times this r minus a epsilon c prime divided by its magnitude. Okay, that's our n hat going to be. So, c prime is not a function of r, the only thing that's function of r is r itself. So, you have an e hat r. Okay, you have an e hat r minus 1 by r. So, you will have a is a constant, you can forget about it. So, epsilon c prime is what will have what you will have here. So, del c prime over del theta e hat theta, and then a minus del c prime with an epsilon del z e hat z, and divided by this vector's magnitude, okay, which will be simply square root of 1 plus epsilon over r del c prime over del theta square plus epsilon del c prime over del z whole square, and this is our n hat. Okay. So, now what we start doing is we are going to linearize. We are going to linearize all equations. So, of course, your pressure will have some higher order terms, but we are not interested in those. So, I am going to linearize everything from here. Okay. I am going to linearize everything from here, and what we are going to get here is, first of all, this is evaluated at r equals capital R, by the way, which is equal to a plus epsilon c prime. Okay. It is not like this derivative is evaluated anywhere in the space, it is evaluated at the interface. That is where we need the normal. Okay. So, you can imagine that these are higher order terms, these are epsilon square terms, all of them. So, I can write in the linearization approximation, I can write this as e hat r minus epsilon over r del c prime over del theta minus epsilon del c prime over del z, this is e hat theta, this is e hat z. Okay. Now, let us compute this del dot n. Del dot n is nothing but divergence of this vector that we have. So it will be simply 1 by r del r of r times the radial component of this guy plus 1 by r del n theta over del theta plus del nz over del z. So the radial component of n hat is e hat r. It's 1 basically. N hat is e hat r. So this is 1. So this is simply 1 by r del r of r. And then you have 1 by r del theta of n theta. What is n theta? Minus of epsilon. Of course, they are not functions of theta. You have r, which is also not function of theta. So r square del c prime over del theta. And then what is nz? Del epsilon del c prime by del z. So minus epsilon del c prime by del 2 c prime by del z square. Yes. How did you linearize n hat I just ignored any terms which have order epsilon square. So for example, you have this 1 by square root 1 plus some epsilon square times something. This you can write as 1 plus epsilon square times something to the power minus half, right? And then when you open it with binomial expansion, you will get this plus order epsilon 4 terms. I am only interested in order epsilon terms. And there's no order epsilon term except, I mean, or higher, there is just one.
But won't the order be reduced because it is under root?
No, that's what happened with this binomial expansion. No, order won't be reduced. Okay, 1 plus epsilon square times something square root is not same as epsilon square times something square root. There is a 1 there. There is a 1 there that is making all the nonsense for you. Okay. Square root of 0.001 is higher than 0.001, it's 0.1. But square root of 1.001 is not going to be higher than 1.001. That's basically what's going on here. So let us take this del dot n. So this is simply 1 minus epsilon over r square del 2 c prime over del theta square minus epsilon del 2 c prime over del z square. Okay. Now notice this r we are evaluating at a plus epsilon c prime. So this is all, I mean, there's still more linearization to do. A plus epsilon c prime whole square del 2 c prime over del theta square minus epsilon del 2 c prime over del z square. Okay. Now here if you look at it, it is again the case you have 1 by a plus epsilon c prime square, which is equal to a plus epsilon c prime to the power minus 2. So this is going to be equal to 1 by a square times 1 plus epsilon c prime over a to the power minus 2. And now you start the linearization that okay, this is equal to 1, this is 1 by a square 1 minus 2 epsilon c prime over a. There will be our higher order terms, but we are not interested in those. Actually, as you will see, this is an epsilon order term. So the only thing that we need from the denominator is order 1 term. We don't need a order epsilon term also, because at leading order this is 1 minus epsilon over a square del 2 c prime over del theta square minus epsilon del 2 c prime over del z square del dot n. This is it. So you can write it like this either. We are not interested in them, or you can say like this. In the exam, you can write both, and of course, after derivation. Without derivation, I'm not going to accept anything.
instead of the 1.
Why?
Del by del
Yeah, you're right. You're right actually. Thanks. And so you will have to linearize that also. So this will be basically 1 by A, 1 minus epsilon C prime over A and so on. This should be 1 by A. You're right. There'll be another epsilon term, right? There'll be another. Actually, we will need this epsilon term. So my bad. This is not it. There is a 1 by A minus epsilon C prime over A square. Yes, plus higher order terms plus this. So del dot n is, so 1 by A was the base state del dot n. Then you have found the corrections minus epsilon of C prime over A square plus 1 by A square del 2 C prime over del theta square plus del 2 C prime over del Z square. We have found these corrections. So this is our scenario. Okay, and now when you substitute it there, so we have P equals P naught plus sigma del dot n. So sigma by A minus epsilon sigma times this guy C prime over A square plus 1 by A square del 2 C prime over del theta square okay. This is what we have. So you can obviously imagine this is your epsilon P prime. Okay. Now let us linearize our governing equation, which is very straightforward actually. Linearization of our governing equation is you have del by del t of, so epsilon del by del t of u prime plus epsilon square u prime dot del u prime plus grad of p prime over rho. Actually, let's write it like so: p naught plus sigma del dot n equals 0. So p naught plus sigma and del dot n is something we have already evaluated, and this is an order epsilon square term, this is an order epsilon term. So you have del u prime over del t plus gradient of, let me call this as p prime. Okay, this is your p prime. This is essentially p naught plus p infinity plus sigma by a plus epsilon p prime. Okay, yeah. So 1 by rho of gradient of p infinity plus sigma by a plus some epsilon p prime. This part is 0, so gradient of this is essentially just gradient of this term, and you have, technically you have order epsilon square terms as well. Now you have 0. This is the linearized momentum equation. Now del dot u prime is very straightforward. That is simply del dot u prime equals 0 when you substitute. Marker. So we have linearized momentum equation, and then we have del dot u prime equals 0, and then we are left with linearizing the kinematic interface condition, and that is basically del by del t of r minus capital R. Sorry, is there a question? What happened?
I was just confusing the symbols.
Which symbols?
Of that P naught.
That's P infinity. This is P naught. There's no P naught now anywhere. Okay. P naught is the base state pressure. Base state pressure is not P infinity. It's P infinity plus sigma by A. Okay. So you can ignore any naught. I hope I don't have it here anywhere, right? I removed it from everywhere else. So
that P equal to P infinity plus sigma del dot n cap is for the perturbed state, right?
no. This is for general. This is general. Okay. This is general. This is again general. P equal to P infinity plus sigma by A is for the base state, because del dot n is equal to 1 by A only for the base state. Here you can see what is del dot n for some perturbations. There is a 1 by A plus epsilon correction. If that correction is not there, if there is no perturbation to the cylindrical surface, that correction is not there. Okay. So del dot n is 1 by A plus some correction, and it's the correction due to that perturbation that we are interested in. Okay, the whole point of this hydrodynamic stability is adding perturbations and looking at dynamics of the perturbations. We are in the linear, we are going to do linear instability only. So in the linear regime, not interested in any other interactions. We're just interested in the dynamics of these perturbations. So here again you have del by del t of r minus a plus epsilon c prime plus, now u is anyway is epsilon u prime dot gradient of r minus a plus epsilon c prime. So from the first term you get minus of epsilon del c prime over del t. Now from here you can imagine what will you get. A is constant, gradient of epsilon c prime will anyways be order epsilon term, but there is already an there is already an epsilon outside, and we are only interested in order epsilon term overall. So the only way you can get an order epsilon term here is if you ignore this and simply del r is what you consider, because there is already an epsilon here. By considering this, a is a constant, so gradient of a will be 0, and this term will only give you order epsilon squared term when it multiplies with this epsilon. So if you are interested in linearization, that is actually easier, because then you get epsilon u prime dot gradient of r plus order epsilon squared quantities. Okay, and from here you get that epsilon del c prime over del t is simply equal to u prime radial component of that, and del r by del r is 1 times an epsilon, or you can cancel the epsilon and you have del c prime by del t equals u r prime. Notice that all of this at the interface. So this part, this is at the interface. Now interface is r equals a plus epsilon c prime. But you notice that epsilon del c prime by del t, if you want to evaluate at r equals a plus epsilon c prime, then as we have done in our flow past a wavy wall, you can do a further Taylor expansion here and write it like this: at r equals a plus epsilon del 2 c prime over del t del r at r equals epsilon r equals a times n r minus a, which is epsilon square times c prime, and so on. So when you open both of these terms, same you can say about this epsilon u r prime, same you can do the trick for epsilon u r prime. So what it means is that instead of applying this interface condition at this complicated interface in the linear approximation, you can apply it at simply r equals a. So even more simplified version of this kinematic interface condition is that don't apply it at r equals a plus epsilon c prime, because this is anyways an order epsilon term. Any further correction that you want to add to it will be order epsilon squared. We are not interested in that. So just apply it at r equals a. And this is very similar to what we had in flow past a wavy wall, where we applied the no penetration condition not at the complicated wavy surface. We applied it at y equal to 0. Okay, and now we have our system of equations that we need. Basically, we have linearized all the equations. So we have a linear system of equations, you can think about it like that. Okay, so you can substitute this p prime here, you can substitute the p prime here, and yet we don't have an ODE, or we don't have a system of ODEs now. We are still stuck with PDEs. So how do we deal with this system of linearized PDEs? And the idea here is to use normal mode assumption. And there are two parts to normal mode assumption. First of all, is it spatial only, or it is temporal, or it is both spatio-temporal? Okay. Now the definition, by definition, this normal mode assumption is that, let us say you have a perturbation of phi in x, y, z and t. Let us say this is a variable, you have its value as some phi naught plus epsilon phi prime x, y, z and t. Okay. And the idea is, if P naught is uniform in x, let us say, so this is for example, okay, not in general. So if phi naught is uniform in x, okay, so uniformity in x would mean that the base flow or the base state is independent of x. Okay, technically we want to say that it is not uniform in x, but we want to say it is homogeneous in x. When was the flow homogeneous in any direction so far in this course? When has the flow been homogeneous in any direction? What has been a uh, peculiar property of that direction, or of the setup in that direction, when the flow we have said, oh, it's homogeneous in this direction because the extent of the flow in this direction is infinity. Whenever we have a direction which is extending all the way to infinity, from minus infinity to plus infinity, basically there are no walls, there are no boundaries from in the flow in that direction anywhere. In that case, we have said that our flow, the base flow that we have been solving for, is homogeneous in that direction. Okay. So, in this case you can write your this phi prime minus infinity to infinity p hat k x y comma z comma t e to the power I k x times x d k x. Basically what I am saying is it is homogeneous. So, that means x belongs to minus infinity to infinity. So, x is an infinite interval. The moment we have a variable which is extending all the way to infinity, you can take Fourier transform. You can write it as a integral of its Fourier transform. This is what we have covered with Fourier series and Fourier transform. Okay. If it was bounded and let us say you had some periodic boundary conditions, then you could have written it as a series of written it as a Fourier series. Now the domain is tending to infinity. This is the same as limit L tends to infinity that we have evaluated, and it is the Fourier transform. And this is called the normal mode assumption that this is the beginning. Let us say this is the beginning of normal mode assumption, and technically this is the beginning of normal mode assumption in space. Now, what about normal mode assumption in time? So, normal mode assumption in time. So, let us say we are interested. So, we are interested in evolution of all perturbations, or rather any perturbation. Okay, we are interested in evolution of any perturbation. What this technically means is we are not really, this is not, we are not solving like it like an initial value problem. Okay, when you have a system of PDEs which have unsteady terms in them, we're not solving them. There are two solutions that you can find. There is a steady oscillatory solution and there is a transient solution. What it means is I'm not interested in putting any perturbation here and then looking at how it is going to evolve in the flow. What I'm interested in is, okay, the perturbation exists, give me the whatever the non-transient state of the perturbation is. Now, non-transient here doesn't necessarily mean that amplitude is going to be constant, but so far in for this course we are going to look at instability when the frequency is going to be constant of that perturbation. So, the idea here is that we are interested in in all time behavior without the transients from a random from any without the transient from any initial condition. Okay, what this means is that this perturbation that we have written as a function of time, I am going to write it as p hat x comma y comma z comma omega e to the power minus omega t d omega. So, basically what we are saying is that the time axis is also from minus infinity to infinity for us. Of course, it does not make any sense for time to be minus infinity to infinity. So, just accept this as for now, that we are looking our time origin at some later stage such that you can assume the flow to be periodic. You can assume the flow to be periodic. Now, the flow might be periodic with respect to constant frequency. The amplitude could still increase. So this is an important point here, that let us say if I give you a signal like this, let's say I give you sine t into e to the power I 2t, or rather not sine t, I give you sine t times e to the power 2t. Let's say I give you this. How is the plot of this solution, this function going to look like? So this is, let us say, sine, okay, but you have the amplitude increasing exponentially, okay. So this is going to look like this. Now the amplitude is increasing exponentially, but the frequency is constant. The frequency is constant. The solution is going to cut the zero axis at same intervals, and that is periodicity for us. Okay, you may not have the same value. Let's say the usual definition of periodicity would require you to have this value. If it has this value here, it would have this value here as well. That is not the case, because the amplitude is increasing in time, but the plot is cutting the zero axis at equal intervals, and that is the kind of solution that we allow for the perturbations to have. Okay, you may get that basically you can see this is going to be looking like some 2 plus it, okay, and immediately you should relate it to what we have been looking for ODEs, that let us say you have some lambda t where lambda is a complex number. You may have a 0 imaginary part of that complex number, it might be purely real. In that case, you will not have any oscillatory part. You may have no real part of that eigenvalue, in which case you will only have frequency, and it will be a constant amplitude function that you obtain for the perturbation. Okay. So this is what we are going to entertain. Basically what I want to tell you is that when we substitute this kind of a perturbation, technically we don't require this omega to be purely real. This omega can be some imaginary number as well. Okay, this omega can be some imaginary number as well. Now some of you may question, okay, what the hell then does this integration mean? For that, what you can think about it as, I'm doing some integration in the complex space, or you can relate this to Fourier transform. So whenever we look Laplace transform, so whenever you have some y as a function of t, if you look at d by dt of this is s time capital Y of s, right? Okay, instead of s I am putting I omega, I am going to put I omega. When I look at my linearized equations, I am going to put, basically what I am trying to do is I am trying to convert whatever derivatives I have into algebraic expressions. That is what our Laplace transform helps us in, right? So whenever you see here in all of these equations and here also, using these normal mode assumptions, I am going to replace the derivatives with algebraic expressions, and in a lot of cases that is going to give me linearized ODEs or even linearized algebraic equations. Here, as you will see, I mean, you will get linearized algebraic equation when you have all directions as homogeneous. Let us say you have a system of equations, all directions are homogeneous. So you can do this in all x, y, z direction, you can write a Fourier transform. So any del by del x will be simply I kx times that, any del by del y will be simply I ky times the Fourier transform, and so on and so forth. So all derivatives you can convert as algebraic expressions if all directions are homogeneous. And in the end then you will get a algebraic expression, not even a differential expression to solve. Okay, what this expression will be, if you saw, if you remember our ODE system, we had linearized the ODEs and then we were interested in the eigenvalue of Jacobian. Okay, that was a algebraic eigenvalue problem that we solved. Okay, that was an algebraic eigenvalue that we solved. Here you will see we can either get an algebraic eigenvalue problem or a differential eigenvalue problem, but ODEs, after using this normal mode assumption, which we will cover in the next class.